Hi, I'm Scott Vaughn. In this video, I'll demonstrate what I call the Vis-Viva Lab. My goal here is to illustrate just one example of using a computer game as a virtual lab to teach and learn math and physics. In this video, we'll use the computer game Kerbal Space Program to confirm conservation of energy and angular momentum for an object in orbit and for objects following suborbital and hyperbolic trajectories. This is done interactively and is dynamic with data collected from the game, just as one might collect data in a lab. I don't want to suggest this would replace traditional teaching methods, but rather that this can supplement traditional methods of teaching and learning. This is an example of experiential learning, and it's also fun, and that's a powerful combination. The observations made here lay the groundwork for further discussion of conservation of energy and angular momentum, and for development of the Vis-Viva equation, something that is fundamental to understanding orbital mechanics. And the math and physics explored here extend well beyond just this application. These principles are applicable to a wide range of situations even beyond rocket science, so exploring and asking questions about these topics leads to a variety of lessons in algebra, calculus, and physics beyond rocket science and open the door to a better understanding in any STEM field. If you find this topic interesting and would like to learn more, I've created a workbook along with other videos and interactives on many topics in math and physics that relate to rocket science and aerospace, and you'll find more at the website sites.google.com/KSP-Math. The Vis-Viva Lab that I will illustrate here is in Chapter 2 in my workbook, and also the Excel sheet that I'm using in this video to collect data and do the calculations, as well as the GeoGebra interactives that I'm using to illustrate conservation of energy and angular momentum, both in the Kerbal system and for the real-life Earth-Moon system. All of this is at my website, and I'll link to that in the description below. The term vis-viva is Latin for living force, and the name comes from the early history of physics when the concept of conservation of energy was first being developed. In this lab, we will launch a rocket into a suborbital flight, and into an orbital flight, and finally into a hyperbolic trajectory, that is, one that escapes the planet's gravity. We will measure the altitude, velocity, and pitch of the spacecraft at different points during flight, and these measurements lead to calculations that will then confirm conservation of energy and angular momentum. This is what's so great about using the game KSP. It provides a virtual lab for experimenting and actively engaging with these concepts. Using these measurements, we will compute specific energy and angular momentum for the spacecraft and confirm these results remain the same at each point during the flight. That is, with different altitude, velocity, and pitch, the specific energy and angular momentum remain constant. Because these values remain constant, we say they are conserved. To keep this video relatively short, I'll focus mostly on the lab aspect, measuring and computing the relevant values. I won't spend time in this video fully developing all the theory. A lot of that theory is already in the workbook that I wrote, and I do hope to return to this topic later for another video and connect this work with the development of the Vis-Viva equation, and explore all the ways these concepts are at the foundation of understanding orbital mechanics. For example, the mathematics behind elliptical, parabolic, and hyperbolic trajectories. But here, today, we're launching rockets, collecting data, and comparing results from the calculations that are based on that collected data. As we measure altitude, velocity, and pitch during flight, we will compute specific energy with this formula. The values used in this formula are epsilon for the specific energy, v for the velocity, r for the radial distance from the spacecraft to the center of mass of the planet or object being orbited, and mu for the gravitational parameter of the planet, moon, or object that is being orbited. We can use this formula for any spacecraft, satellite, moon, planet, orbiting a larger mass in a two-body system. The formula for specific energy combines kinetic energy and potential energy of the orbiting body, and is called specific energy because it represents energy per unit mass. It's important to observe this formula does not include the mass of the orbiting body. Instead, given the speed v, the radial distance r, of any orbiting body, all that's needed is the gravitational parameter mu for the body that's being orbited, be it a planet or moon or star. Note also that we could use mu equal g times m, where g is the gravitational constant, 6.67 times 10 to the negative 11, and capital M is the mass of the planet or moon or star that's being orbited. And I hope it's clear that this formula works also in real life to calculate specific energy for any spacecraft or satellite or moon or planet as it orbits about another celestial body. For example, the moon orbiting Earth, or the Earth orbiting the sun. It's the same math and physics in real life as it is in the game KSP. The reason we use KSP is because the game can work as a virtual lab, where we can interact directly with a dynamic system that models these real-life principles. And in the virtual lab, we can pause the game to take measurements and discuss the issues. And it's fine if we blow stuff up. And in the process, because the math and physics used here are the same as would be used in a similar calculation in real life, we can better understand those real-life examples. Now, to compute specific angular momentum, in real life and in KSP, we will use the formula here, h equals rv sine theta. Technically, specific angular momentum is a vector, and here I'm only calculating the magnitude of that vector, but that's all we'll need for our purposes here, just the magnitude, a single number, not the vector itself. And the values used here in this formula are h is the specific angular momentum, r is the radial distance from the spacecraft to the center of mass of the planet that's being orbited, v is the velocity, and theta is the angle between the radial vector and the velocity, as shown here in the graph. And then finally, because we have computed values for specific energy, epsilon, and the angular momentum, h, we can determine orbital eccentricity, E, using this equation. Here we have E as the eccentricity, epsilon is the specific energy, h is the specific angular momentum, and mu is the gravitational parameter of the planet or moon or whatever object is being orbited. And then based on that eccentricity, we can confirm the type of orbit or trajectory that's being followed, as shown here in this table. There are a few other things I should mention before we launch right into the data collection. First, we'll measure velocity, altitude, and pitch, and from that we compute specific energy and angular momentum. But to compute angular momentum, we need the angle theta, which is the angle between the radial vector and the velocity vector. I have those illustrated here as the vector r and the vector v. We find that angle theta by subtracting the pitch from 90 degrees. This is because the pitch is the angle between velocity and the local horizontal, and the local horizontal is perpendicular to that radial vector. And to get a useful value for pitch from the nav ball display in the cockpit, we need to orient the spacecraft in the direction of travel, which is called the prograde vector. Also, we measure altitude, but we'll need to add to that distance the radius of the planet or moon that's being orbited. This is because our formulas use r, which is the distance between the center of mass of the primary body and the orbiting body. Okay, now just a few last details before we launch. One of those would be that we can see that our speed is indicated here in the nav ball. Right now it's at 0 meters per second because we still haven't launched yet. But what I'm going to do is click that one time so that it shows the orbital speed. And actually what that's measuring is the speed that we're traveling around the center of the planet, because the planet is rotating, is spinning on its axis. And we're traveling around the center of the planet at 174 meters per second. At this point, we are near the equator of the planet and traveling around the center of the planet as it spins on its axis. So that's our current speed relative to the center of the planet, and we'll need that as we measure our speed in order to calculate energy and the orbital energy and the angular momentum. Another thing we could adjust here, it won't matter that much, but we could measure our altitude relative to sea level. Still, we need to add on to that the radius of the planet. The radius of the planet is 600,000 meters. So the altitude is measured in meters, and adding to that the radius of the planet, that gives us our distance r from the center of the planet, and that's also what we need to calculate orbital energy and angular momentum. And another thing would be measuring the pitch, and I can measure the pitch by looking at the angle here that's indicated in this nav ball display, and you'll start to see that moving as we pitch over after we launch straight up and start to pitch over to reach orbit. I think this first launch we'll just go for a suborbital flight, and you'll see that I'll be measuring the angle from the nav ball here. And I'll be careful to get, so here's an indicator for the prograde vector. So I'm going to want that indicator, the direction that I'm pitched, to be lined up with that prograde vector so that the pitch actually is the direction that we're traveling. So we can use that in our calculations as well. I think that's it. Are you ready, Bill? Looks like it. Okay, let's go. Okay, so I paused it here, and looks like we're lined up with the prograde vector, and I've got a current altitude of 45,045 in meters. The velocity currently 885 meters per second. And for pitch, I'm going to estimate that to be, well, it could be about 70, maybe just slightly under that. But I'll just go with 70 degrees pitch, and therefore the theta is 90 minus 70, so this would be 20 degrees. Okay, and we'll come back and fill in these in a moment, but let's get another point, and maybe just another point as we're coming down. And what I want to do is make sure that I'm actually pitched in the direction that we're traveling as we're coming back down. But then I'll want to reorient so that we've got the blunt end of the capsule facing the oncoming air, because it's going to heat up the capsule. So I want to reorient retrograde as we're coming in, but to take the reading, I still need to be pointed in the direction that we're traveling. There's a picture of our current trajectory reaching an apoapsis here at about 88,610 meters, 88,000 meters before coming back down. Now, this should actually be an elliptical orbit, even though it intersects the surface. In the entire path, it'll be an elliptical orbit. If we traced it out mathematically, it would form an ellipse. So we've kind of like gone over the highest point in the trajectory, and we're starting to pitch now downward. Certainly have slowed down quite a bit. So really, I could take a measurement at any point. So how about there? So at this second point, I have an altitude of 84,688 meters with a velocity of 385 meters per second. And I'll say that pitch is about negative 40 degrees. So if we do 90 minus negative 40, that's 90 plus 40, and so that makes it as 130 degrees. Theta is 130. And we'll go in and do the calculations in a moment to get those values and then determine what the eccentricity is. But let's complete the flight. So, yeah, for safety reasons, why don't we turn around retrograde so that we're coming into the atmosphere with the blunt end there of the capsule to take all the heat of the drag. Okay, back here at the KSC, let's run through those formulas just really quick with those numbers. This is from the first point in the flight where we had a velocity of 885 meters per second and an altitude of 45,045 meters. I'm adding that onto the radius of the planet in order to get that value r. This is the value mu for the planet Kerbal, and putting it in the calculator, I get about 5.08, negative 5.08 times 10 to the 6. Actually, one other comment is that when we are in bound orbits, we will have negative values. So that this potential energy is greater than absolute value to this term that involves, that comes from the kinetic energy. So you can see that when it goes to a hyperbolic orbit, this will become a positive, but in all the bound orbits, we expect negative, so that's what happened there. So negative 5.08 times 10 to the 6 meters squared per second squared, that's the specific orbital energy at that point in the flight. I would expect it to be the same thing at point 2. And then in order to get the angular momentum, I'll take the radius of the planet, add the altitude in meters. That's the value that I'm going to put into the formula for r. There's the speed again, 885 meters per second. There's the angle theta that comes from measuring the pitch at 70 degrees. I've got theta equal 20 plugged into the calculator. I get about 1.95 times 10 to the 8 meters squared per second as my angular momentum. And then at this point, we'll just put those formulas into Excel, and we can just do them quickly here. So once again, just checking those numbers. 45,045 meters in altitude, velocity 885 meters per second, pitch of 70 degrees, and yeah, so now we can fill in those numbers, confirming that they are the same thing. That I got doing this calculation by hand. Everything looks good. So yeah, so then we can now take point 2 and use the same formulas. Let's speed it up. Let's put it into Excel here. So at the other point, on the way back down, altitude was 84,688 meters with a velocity of 385 meters per second and a pitch of negative 40. Okay, so the specific orbital energy is really, really close, and the angular momentum, they're not exactly, that's very close. This is 1.95, 2.01, 2. So I didn't expect it to be necessarily exact. There's a lot of things that can contribute to them being a little bit different. I mean, for primarily probably the angles that I measured is not precise. Another thing that can happen is that as you go through the atmosphere, that can cause drag, and as an external force that can change the angular momentum and specific orbital energy. And also, if you fire the rocket at any point between points where you take measurements, that's an external force that would change the orbital energy angular momentum. So I think that it's most likely it's just a matter of accuracy in the angles that contributed to the difference there. And I see that both of these come out with eccentricities that are just a little bit less than 1, which is what I expect, an elliptical orbit. So now, of course, we did get slightly different values because we have slightly different values here, but what we could do to resolve that is either perhaps take an average or just write to the level that they are both, the accuracy that they are both the same. So I think I'll do that. I'll just say that it's about 0.98. The fact that it's less than 1, I know that it is an ellipse. Okay, so now we can do an actual orbit that is outside the atmosphere and take 2 points there and see how that goes. Are you ready, Bob? Let's go. Now we can just coast up to the apoapsis and then fire the engines again to get into an elliptical orbit. So around that point, when I reach the apoapsis. As we near that, I'll fire the engines again to increase the periapsis so that we actually have an orbit that's completely outside of the atmosphere. Okay, so here's the orbit, 84,607 meters for the periapsis and about 855,975 meters for the apoapsis. Well, the idea now will be just to take two measurements at two different points during this orbit. Okay, see altitude 734 kilometers, that means 734,000 meters. Speed is 1411 meters per second. Pitch about 16 degrees, and therefore theta is about 74 degrees. Okay, altitude 782 kilometers, velocity 1345 meters per second, pitch about -15 and therefore 90 minus -15, about 105 degrees for theta. Typing in the data from both points into Excel, we can confirm orbital energy and angular momentum are the same at each point, and the orbit eccentricity is about 0.37. Now, let's confirm conservation of energy and angular momentum in a circular orbit. Once we've achieved any elliptical orbit, given enough remaining fuel, we can circularize the orbit by firing the rocket engines at the apoapsis, which is the farthest point in the orbit, to accelerate the rocket in the prograde direction. This has the effect of raising the altitude of the periapsis, which is the point closest to the planet. With practice, patience, and enough corrections, we can reach a very nearly circular orbit, where both apoapsis and periapsis are nearly equal. In this example, both at about 95 kilometers in altitude. In the circular orbit, we can observe that altitude remains the same at each point, as does the speed. We observe pitch is about 0 degrees in a circular orbit. That is, our prograde velocity or direction of travel is parallel to the local horizontal and perpendicular to the radial vector. In this example, we confirm orbital energy and angular momentum are conserved. The values are essentially the same at each point. We observe also that the orbital energy is negative, indicating that it's a bound orbit. And the eccentricity is nearly 0, indicating the orbit is nearly circular. Now, let's test out conservation of energy and angular momentum in a hyperbolic orbit. Okay, let's prepare for a hyperbolic flight, and out of concern for the well-being of the crew, I decided not to include any crew. This is an uncrewed rocket that allows me to control it from the ground. And before I go into this hyperbolic orbit, one of the things that might be really interesting to observe is that we would reach hyperbolic orbit once we are on an escape trajectory. So that means that we're traveling initially faster than the escape velocity. So what is escape velocity? It's exactly when this specific orbital energy that we've looked at, when that's equal to 0. So let's set this equation equal to 0 and solve for the speed, v, that's required to reach a hyperbolic orbit, to reach escape velocity. What would be the necessary speed to be on a hyperbolic trajectory? Would be any speed faster than that. So if I set the orbital energy to 0, move this term over to the other side, write it in this way, multiply both sides by 2, take a square root. Of course, there's plus and minus solutions algebraically, but I'll just take the positive as the speed that I would need in one direction or the other to be traveling at this speed. And then if I take the gravitational parameter for Kerbal, take the radius of the planet, and let's just pick an altitude of 100,000 meters. So we have a radius of 700,000 meters, and plug that into this formula, and I can see that it's about 3175 meters per second is the required speed to escape the gravity of Kerbin if I started at a 100-kilometer altitude. So what we could do is launch up into an elliptical orbit or a circular orbit at about 100 kilometers, and then look for any speed that exceeds that, and at that moment we will see the path switch into a hyperbolic path that will escape the gravity of the planet. All right, so now let's give it a try. Well, at this point, my orbit is pretty near to an altitude of 100,000 meters. So let's just accelerate up close to escape velocity, see if we can get past that, and we'll see the orbit turn into a hyperbolic orbit. I can see at this point that it is an elliptical orbit. And as I increase the speed, the apoapsis will go further and further away until finally it turns into a hyperbolic orbit and we're on an escape trajectory. So there, as the rocket is firing, the apoapsis is going further and further away, that apoapsis being the farthest distance we would reach at our current speed. So it's extending further and further out. I calculated it was about 3175 meters per second when it hits the escape velocity, and there we are reaching 31, basically right there. So now we're on an escape trajectory. Okay, so now we'll just pause the game and take another data point. Altitude 146 kilometers. Velocity 3222 meters per second, pitch 12 degrees, and theta 78 degrees. Point 2, altitude 2,121 kilometers, velocity 1873 meters per second, pitch about 64 degrees, theta 26 degrees. Okay, and that's it. That's the end of this video. If you found this interesting and would like to reproduce these results in your own experiments with the Vis-Viva Lab, I'd like to suggest a challenge to leave you with. Try out the suborbital flight, but when you create the elliptical orbit, create one that intersects at the Mun, one of Kerbin's moons. After being captured by the Mun's gravity, circularize your orbit around the Mun and confirm conservation of energy and angular momentum there around the Mun, and then create a hyperbolic orbit to exit the Mund's gravity, confirming orbital energy and angular momentum for the hyperbolic orbit as you exit the Mund's gravity. And then, hopefully, return home safely. And I hope you found this video fun, inspiring, and educational, and thank you very much for watching.